Okay, this video briefly explains the rich regression and LASSO in simplified terms. Rich regression and LASSO allow us to include all predictors in our model and still avoid overfitting, and this is done by constraining or regularizing their coefficient estimates and at times strings the coefficients estimates towards zero. And oftentimes we have the 1 in 10 rule in any kind of regression, and this 1 in 10 rule means that one predictor or one independent variable can be used to assess no more than 10 observations or cases. That's the meaning of 1 in 10 rule. You can Google that in layman's term. And the purpose of 1 in 10 rule is to minimize problems associated with model overfitting. The rich regression seeks to provide the best fit to the coefficients, and by shrinking the values of the regression coefficients towards zero. And as you can see from this equation, there are two main components to the rich regression. The first component is similar to the ordinary least square regression, and the first component is the error sums of square or the residuals sums of square. And the second component is not found in the ordinary least square regression. The second component is only found in rich regression or LASSO. The second component would be the lambda or the shrinkage penalty. And we call all these beta square the regularized terms. And you will see in the subsequent slides why all these absolute values of beta for LASSO and squared value of betas for rich regression are called regularized terms. And the rich regression seeks to provide the best fit to the coefficients, and this is done by shrinking the value of the coefficients towards zero. This is what regularization means: to circumvent problems associated with overfitting, or to circumvent the 1 in 10 rule. Sometimes the betas or coefficients have to be regularized. Their values have to be string to provide the best fit to these coefficients. So, as you can see from the equation below, there are three steps involved here. First, we square the values of the betas. We then sum the squared values of the beta up. And finally, we multiply the squared beta values by the lambda. The reason for doing this is to control the impact of the betas and at the same time try to simplify the model as much as possible. And be mindful that the lambda or the shrinkage penalty does not apply to the intercept or beta 0. When the lambda is 0, the penalty has no effect, as the lambda gets larger, the impact of the shrinkage penalty grows, and the beta estimates will approach zero. As you can see, the ridge regression facilitates a way to fit the model with all the variables we may need for our analysis, because we have to base on a certain theoretical framework or due to other reasons. And because of that, we cannot exclude any of these variables from our model. And because of that, our model may be prone to overfitting, or we may violate the 1 in 10 rule. And because of that, the ridge regression is used to fit the model with all the needed variables, while we can circumvent the 1 in 10 rule and prevent overfitting. Cross-validation is used to determine the optimal value of the lambda. We call that the best lambda, or the value of the lambda that provide the best fit to the coefficients. And you can check out my video or other videos on K4 cross-validation on YouTube to get a better idea about cross-validation. The ridge regression seeks to minimize the impacts of irrelevant variables by shrinking the estimates associated with each beta, or to make them lower, but not the intercept. The ridge regression does not intend to shrink the estimates associated with each beta all the way to zero. In other words, to get rid of them. Increasing the value of the lambda will result in a reduction in the estimates associated with each beta, but the betas will never be excluded or reduced to zero. Because the ridge regression does not shrink the estimates for each beta to zero, it can be hard to interpret the model, especially when we have many predictors or independent variables. And because of that, LASSO, we are going to introduce this technique later, is another extension built to regularize linear regression, but with a small twist. The only difference between the ridge regression and LASSO is that the regularized term for LASSO, as you can see from the equation below, is in absolute value. LASSO, which means least absolute shrinkage selection operator, overcomes the disadvantage of ridge regression by setting the high beta values to zero when these betas are extremely large or approaching infinity. And if these betas or variables are not relevant to the purposes of our analysis, these high beta values can be set to zero. And because of that, we can say that LASSO works in a similar way to the best subset selection regression. Here, we try to control the impact of the betas and At the same time, we try to simplify the model to the best we can by first summing the absolute values of the beta and then multiply them by the lambda. And these are the determinants of the number of cases for the coronavirus in Nebraska. And analysis were being done using the ordinary least square regression, the ridge regression, and LASSO. And as you can see, the estimates for the betas do not really make sense for the OLS and ridge regression. And as you can see, the betas or the estimates for the betas were being string in ridge regression, and irrelevant betas were being reduced or string to 0 in LASSO. So, as you can see from this table, results from ridge regression may make more sense than results from ordinary least square regression, and results from LASSO may make more sense than the ridge regression and the ordinary least square regression. In other words, the ridge regression or LASSO may be more appropriate than the OLS regression if we want to assess the determinants of the number of confirmed coronavirus cases in Nebraska. Here are the R syntax for the OLS regression you just saw from the table in the previous slide. I first conducted an ordinary least square regression. Then I get the data ready for ridge regression and LASSO. And here are the syntax written in R for ridge regression and LASSO. And here is another analysis on coronavirus in the state of Louisiana. In this analysis, I attempted to assess the impacts of different pre-existing social demographic conditions on the number of confirmed cases in Louisiana. And I conducted my analysis in ordinary least square regression, ridge regression, and LASSO. As you can see, for the results obtained for OLS regression, some of the estimates for the betas are kind of bizarre. They are somewhat large. And if you see, if you look at the third column in this table, when analysis was conducted in ridge regression, it shrinks the value of the coefficients somewhat. If you compare the second column of this table to the third column of this table, and I conduct my analysis in LASSO, and when analysis were being conducted in LASSO, it shrinks a lot of these so-called irrelevant variables to 0. And in my humble opinion, the estimates for the betas, they make more sense under LASSO. And here is a continuation of my analysis. Because I think I used about 23 variables, they are too big to be fit in one table. So because of that, I have two tables for my analysis using ordinary least square regression, ridge regression, and LASSO. And as you can see, ridge regression shrink the estimates for the beta, and LASSO reduce irrelevant variables in the model to 0. So that's the difference among ordinary least square regression, ridge regression, and LASSO. And here is just the R syntax for the potential impacts of pre-existing social demographic conditions on the number of confirmed coronavirus cases in Louisiana. And as you saw from the table for Louisiana in the prior slide, I use county level data. And here is the R syntax for the ridge regression on county level data in Louisiana. And this is just the R syntax for LASSO for the same county level data in Louisiana. I just use.